Okay. So, we have seen few types of modulator to generate just multiplication of two signals. Now, what we have promised that we will try to see the relative advantage and disadvantage of these things. Now, we are actually coming into the engineering part of it. So, let us say the previous one that we have done, there we have got the output as 4b mt cos omega ct. If we just multiply, we get mt cos omega ct, right. So, these are the three things we are getting. So, what is happening if you just carefully see, especially this one, when I am doing multiplication, think about my power. Most of the power, because it was having the infinite Fourier series representation, many part of power has gone to 3fc, 5fc, 7fc and all those things. So, those power, because I just employ a band pass filtering, those things are all wasted, right. So, that is why I am getting a pretty low power 2 by pi, which is getting linked over here, right. So, that is one disadvantage of doing this. Okay. So, if I do with a switching circuit, I will be actually leaking power into higher harmonics. So, effectively I will be losing power, and that is very important, because whatever power I put, I want to actually employ that for my modulation purpose only. Those are all getting wasted. So, it is very important that I carefully design my system, and that is why probably people have tried to employ direct multiplication instead of doing this circuitry. Okay. So, that is one aspect of it, that we should think of directly multiplying it if we can. Okay. And that is why there are devised multiplier chips which we will be generally using for multiplying this signal. Okay. Nonlinear one also is quite alright, as long as my B is not very small. If the nonlinear device means there the biasing is very sensitive. If the coefficient becomes too small, especially that quadratic related to that coefficient becomes too small, then probably again this will be very low, and I will be most of my power will go into the linear part, which is anyway getting cancelled out. Okay. So, that is also very important. Okay. So, after this, let us try to see another form of modulation. Okay. So, the other form of modulation is called, that is actually termed as AM, because historically that came before, amplitude modulation. So, you can call that as DSB with carrier. Okay. So, that will also have double sideband, but the carrier will be present. What does that means? So, that means you were earlier generating mt cos omega ct, I will add a carrier to it, which is pure carrier A cos omega ct, where A is the amplitude of the carrier. So, this is what is amplitude modulation. So, it is a very simple one, but you will see that a lot of advantage you will get out of this, and this is being employed for broadcasting generally, because the corresponding receiver becomes very simple. So, we just add a carrier to it, and you will see that the entire complicacy of recovering carrier and then multiplying with a carrier just vanishes. How? We will see now. So, if I just do this, I can write it as A into mt cos omega ct, right. So, what is happening? It is almost like a DSB SC, it is just my mt is DC shifted. So, whatever message signal I have, suppose I have a message signal something like this. Okay, so this is my mt, corresponding some MF I have. Now, if I directly do modulation the way I was doing DSB SC, what will happen? This will create envelope, and then there will be a carrier, okay, and every 0 crossing there will be 180 phase shift. This is something we have seen. Now what we are doing, this empty we are adding a DC to it. So basically this will be, that's, let's say that is A, so empty will be over this, and suppose this is the minimum which is called minus MP, okay, the minimum voltage of my empty message signal, and somehow my A is greater than this MP. Then the entire signal will be above 0 level. So basically what I am trying to do is, I am trying to avoid any 0 crossing. That is all I am trying to employ over here. So by doing this, that means adding carrier actually means that in the message signal I am adding a DC term. And why I am doing that? Because I knew that whenever I will be multiplying by cos, if there is a 0 crossing, there will be a phase reversal. I want to avoid that phase reversal for good reason, we will come to that. But once we avoid that phase reversal, what will happen? Now if I multiply this with cos omega ct, my envelope will look like this, and inside the carrier will be flowing. And we know that we have avoided 0 crossing, so there will be no 0 crossing inside, okay, and there will be no phase reversal inside. Fine. Why this is so much advantageous, or what is the advantage of this and what is the disadvantage of this? Let us try to discuss that. First, the advantage part. The corresponding demodulator will be much more simplified. So let us try to see what kind of demodulator I can put for this. So what I will do, I will actually, for the demodulator, I will pass it first through a diode. I am completely changing the demodulator now. I am no longer multiplying it with cos omega ct. I know that multiplying with cos omega ct will still give me result, but I do not want to do that. I am just simplifying it. So I will pass it through a diode. What diode will do? This, it will act as a half wave rectifier, right. So only in the positive half it will pass the signal, negative half it will make it 0, okay. So it will just almost take out this half where it is less than 0. So that part it will take out. After passing it through a diode, what I will do is I will pass it through a low pass filter, and then I will pass it through a capacitor followed by a resistor, which is just nothing but a DC blocker. We will see why that is required. And that will give me my empty, or very precisely I will get 1 by pi empty, as long as I am putting this A plus empty cos omega ct over here. That means amplitude modulated signal. If I put it over here, if I just do this circuitry, I will get this. So let us try to prove that. Okay. So let us see, whenever I pass it through a diode, what is exactly happening. So I have this signal, once I pass it through a diode, it is just taking the positive half, and the negative half it is taking out. It is again taking the positive half, negative half it is taking out, again taking the positive half. What does this means? This almost means this signal multiplied by a pulse train, which is exactly synchronized with this cosinusoidal, isn't it? It can be represented as this, because I am sending this signal, only the negative half is going off. That means in the negative half, if I have 0 and multiply this, it will become 0, and in the positive half, if I keep 1, it will just represent that signal. So basically this after diode, or the diode can be represented as a multiplier, which will just multiply the signal whatever is coming, A plus mt into cos omega ct, multiplied by a Wt, where Wt is represented by that pulse train, which looks like this. Remember, for the pulse train, it should be having 50% duty cycle, because for a cosinusoidal I have to take the full positive half and I have to negate the full negative half. So, it must be 50% duty cycle pulse, that is the first thing. Second thing is this time period must coincide with the cosinusoidal time period. So, I had this 1 by fc time period, that must be this t. Okay. So, that should be exactly equivalent, and that is automatically happening because diode is doing that. I do not have to really bring a signal which is of this nature. It is actually the diode characteristics is almost like this omega t as if completely synchronized with the signal getting multiplied, right. So, I can write my output as A plus mt cos omega ct, which is my original signal, multiplied by Wt. That is the output of the diode. I can write this. Now, this Wt I can again expand in Fourier series. This signal I can expand in Fourier series. So, I can write that Wt instead of Wt I can write again that expansion, Fourier series expansion, which we have seen just few means in the previous class probably. So, half 2 by pi cos omega ct minus, or I can keep 2 by pi out. So, 1/3 cos 3 omega ct plus 1 by 5 cos 5 omega ct and so on. Now, just do the multiplication, what I will get, this A plus mt into cos omega ct into this one, that is the first term. Second term will have A plus mt cos omega ct into 2 pi into this cos omega ct. That will give me actually one baseband part and the other higher frequency part, and all other multiplication if I see, that will be all either at omega ct or some higher harmonics of omega ct. So, if I just pass it through a low pass filter, only that part will come out, which is nothing but it is 2 by pi into half will be there. So, half into 2 by pi into mt will be there, plus there will be all other harmonics. If you just multiply all these things, you will just see there will be all other harmonics, some terms into mt into cos omega ct and cos 2 omega ct, 3 omega ct and all those things. Okay. So, I will only have this part. Now, if I put low pass filter, which will take out all these harmonics, which will give me just this, which is 1 by pi mt, right, sorry, mt plus a, that should be this term remains the same. So, mt plus a into 1 by pi. So, at this point after low pass filter, I will be getting 1 by pi mt plus a DC term. Now, this capacitor resistor, that will just act as a DC blocker. So, it will just block the DC, that A part, I will get 1 by pi mt. So, what has happened? The wonder that has happened over here, my receiver circuit has become very simple. I just have to put a diode, no complicated carrier tracking, I do not have to do that carrier tracking, because automatically the diode is doing the carrier tracking for me. You see where that cos omega ct multiplication is happening, over here. I had this term, earlier I was deliberately multiplying it with cos omega ct. Now, diode is actually helping me to multiply it with Wt, which has a cos omega ct. Okay. So, basically my signal itself is carrying the carrier, which I have told earlier also. So, it has the carrier information, but in such a way it is now carrying that with a diode I can actually do the multiplication and I get everything out, I do not have to do any synchronization. You know why this is happening? Because this is a periodic signal, Wt I can write as a periodic signal. If there was a random phase reversal which was happening in DSB-SC, then what will happen? Let us see, I have a random phase reversal. So, my signal was like this, I do not add any DC. So, what will happen? Within this will this will become my envelope, and within this there will be a cosinusoidal which will be just having a carrier flip over here. Now, I pass it through a diode. What will happen? Diode will be that Wt corresponding to that diode, it will be positive here, negative here, positive here, or I should say positive here, 0 here, okay, because it is taking out all this negative cycle. But here there is 180 phase reversal, so there will be positive followed by positive, that is breaking my periodic nature, right. So the WT I will be multiplying, that is no longer periodic, that is a random signal now, because where that crossover will be happening I do not know, that depends on the signal. So anywhere it can happen, so that completely breaks out my periodic nature of WT. So at that point I cannot write my WT as this one very nicely. So therefore that multiplication I was getting, I am not sure now, and that is the reason why I will not be getting my signal back if I just put a diode. So that diode detection, diode followed by low pass filtering detection can only be possible if I put a DC term, so that my entire message signal goes into the positive half, and whenever I do modulation, no zero crossing is there in the envelope, and correspondingly no phase reversal is happening. As long as that is happening, I know my diode detector will be a good multiplier. You can also think about this, see this thing is carrying the carrier information, but let us try to see how I can extract the carrier. So basically whatever is coming over here, I can excite a this thing, a sinusoidal generator by this, but what will happen after some time, the excitement will be given by this, which is a phase reversal. So that will just counteract on the exciter. Whatever excitation it was creating a sinusoidal, now it will just be a phase reversal version of that. So it will just counteract and it will actually negate that thing. So basically if I on a long term basis I wish to track the carrier, I will not get anything, because it will keep on reversing and I will keep on denying my carrier generation process. So that is what happens whenever we do DSBSC. So DSBSC carrier recovery has to be done completely separately. We cannot really employ these things. Whereas if we just add that A term into it, wonderful thing happens and my receiver becomes very simplified, because in the receiver I just get a diode followed by low pass filtering. That is it, nothing else is required. The same receiver we can also employ, or we can also think that receiver in a different manner. So suppose I have my AM signal, which is mostly this is called the envelope detector part, which is mostly employed. So I will be putting a diode on this, okay, and then followed by a kind of charging and discharging path, and here I will be taking the signal out. That is my receiver. So what is happening over here? Let us say I have this signal, of course it has to be AM. So let us say I have this signal, and inside I have this carrier. Okay. Now whenever it passes through diode, I will be just getting rid of this. So I will be getting this positive half, and then see whenever the diode is on, this thing will pass it through it, and probably what will happen, this capacitor will get charged through this, okay. So if diode internal resistance I assume to be very small, so this RC value will be sufficiently small to make the charging time constant very quick, it will be charged very quickly, okay. So this is the charging path. Whenever diode is in reverse bias condition, then this capacitor is not getting any supply, so it must be discharged, but it does not get any path through this diode because diode is in reverse bias condition. So it should be discharged through this path. Now if I design my R and corresponding C in such a way that while discharging it just tracks the envelope, okay. So basically what is happening, I have this, so while charging it quickly charges, whenever diode is on it follows the carrier, very quickly gets charged, but while discharging, if the discharging time constant also is fast, that means this RC value is in such a way designed that it is also faster, then it will discharge full way. But basically to receive my message signal, I want to detect this envelope, because that envelope only carries my message signal. So what I wish to do is, while discharging, it does not get discharged very quickly. Again next cycle comes back, then the diode gets charged, so it again gets charged quickly, but while discharging again it follows a slower path. It is not discharging very quickly. Then what will happen? It will just keep tracking the envelope. Okay. If the discharging time constant is too slow, then what will happen? If you see this negative slope, then the discharging time constant will be too slow. That is also something which I have to take care of. The discharging time constant should be such that I will be always tracking the envelope. To do that, I have to design my RC. So basically what should happen, this RC must be greater than or much greater than 1 by WC, okay, so that it does not follow the carrier, but it must be less than my 1 by 2 pi B, where B is the highest frequency that I can have in my message signal. So this envelope. So this RC must be less than that, so that whenever it is getting discharged, it is not even slower than my slope of the message signal. So as long as I am actually considering this particular condition, because B and WC are known, whenever I am doing modulation, I know with what frequency I am modulating, and I also know what is the, if the signal is, message signal is band limited, what is the maximum frequency that it contains. So if I know these two parameters and if I know this condition, I will be accordingly designing my RC, and immediately I know that it will be tracking my envelope. So finally my signal will look like some which is almost tracking the signal, right. After that there are some aberration, just a low pass filtering will do this, will make it smoother. Okay, so immediately I get this. So this followed by another low pass filtering probably will smoothen the envelope, and of course there should be a DC blocker. That has to be there, because this will, whenever I track the envelope, that will have a DC term. I should have a DC blocker. So immediately I get back my message. So there are two circuits that we have discussed. One was diode followed by a low pass filter, almost employing similar technology, or I can think it from time domain. So that is two representation. One, I was thinking in frequency domain, that my diode generates a signal which has all components, all harmonics as well as the baseband. That is why I was employing the low pass filtering, so that all other harmonics are rejected. And after that I knew that it is A plus empty, so I was putting a DC blocker. Here I am actually seeing it from time domain, so that is why both the representations are good. So I am seeing it from time domain. What I am trying to see is, in the time domain, whenever I pass it through a diode, it is actually just giving me the positive half. Next, it just has to track the envelope. So for that I need a very faster charging and very slow discharging time constant. That is what I have devised, and immediately we could get the envelope tracker. After that it is some low pass filtering, DC blocking to smoothen the signal according to my requirement. Okay. So this gives a very simplified way of demodulating, and this particular modulation technique for that reason is, as we have seen, that it has a carrier. So just if we now try to see the frequency domain representation of the modulated signal, which is A cos omega ct plus mt cos omega ct. If I do a frequency domain representation, this mt cos omega ct, of course that will be half m f plus fc plus half m f minus fc. This is all right, but this cos omega ct, that will be 2 delta function, right. So this will be a by 2, a delta function at plus fc, delta function at minus fc, right. Sorry, plus. So basically if I just try to draw the spectrum, what will happen? At fc there will be these two term, mf term and there will be a delta function which is actually eventually representing the carrier. So that means it has two sideband like earlier one, but it also has this carrier term. So that is why it is called just DSB or AM. I am not suppressing carrier, whereas in the other one I was actually deliberately suppressing the carrier. I was just sending the multiplication term, I was not putting the carrier into it. But I know now the difficulty for the receiver if I do not transmit the carrier. But is it all rosy? In the next class we will probably prove that is not the case. Whenever we put a carrier, we are again sending unnecessary signal. Due to that, there will be extra amount of power I will be sending. So the overall power efficiency will be lesser in this system. And that is why probably you will see the transmitter has to release more amount of power to get similar kind of effect at the receiver. So that means transmitter has to employ some power amplifier and all those things. Okay, so because it has to transmit huge amount of power. So transmitter becomes more, means engineering design wise more complex and more costlier. So we will try to, in the next class we will try to see that how for AM the transmitter is costlier, which was our design target, that I want to, for a broadcasting system I want to make the transmitter little costlier, whereas the receivers will be much more cheaper. And for point to point I want to make the transmitter little bit cost effective and receiver similarly costly. Okay. So we will see that part also, that this has one advantage but there will be another disadvantage into it. So once we have done that, in the next class we will go towards more bandwidth efficient modulation, amplitude modulation. Those are like single sideband. We are now transmitting double sideband. We have already discussed that both the sidebands are carrying equal amount of information. So we do not need both the sideband. So we will try to see some more bandwidth efficient modulation like single sideband, which is called SSBSC, single sideband suppressed carrier. Again we will not be transmitting carrier, or there is something called vestigial sideband. We will see the application of these two. Some cases like for voice you can employ single sideband, whereas for video you cannot employ that, you have to go for vestigial sideband. So we will see that, and its single sideband probably will be the most bandwidth efficient, whereas vestigial sideband will be less bandwidth efficient. There is also another modulation scheme which is also bandwidth efficient, which is called quadrature amplitude modulation. That also we will discuss, and we will see the relative advantage and disadvantage of them.